So let's do an example of finding the absolute extrema involving an absolute value expression. So here let's let f of x equal x squared plus the absolute value of 2x plus 1. Let's find the absolute extrema on the interval -2 to 1. So recall from the earlier pre-calc review that implicit in every absolute value function is really a piecewise function. In other words, what I can write is that the absolute value of 2x is really equal to it's equal to 2x for x greater than or equal to 0, but it's equal to negative 2x, that a little neater, negative 2x for x less than 0. So what that means is that I can actually sort of rewrite this as a piecewise function, and then we can proceed as we did before. So here what we'd say is that f of x is equal to x squared plus 2x plus 1 for x greater than or equal to 0, and it's equal to x squared minus 2x plus 1 for x less than or equal to not 1 to 0. So now we can go ahead and write the derivative. So here we have f prime of x is equal to, we've got 2x plus 2 for x greater than 0, and we have 2x minus 2 for x less than 0. We are not sure at this point, does the derivative exist at 0 or not. If you plug in 0, in other words, recalling what we said earlier, just plug the transition point into both expressions, and what we'll see is that in the first expression we have 2 times 0 plus 2 gives positive 2, and in the second expression we have 2 times 0 minus 2 gives negative 2. So we in fact have a slope of positive 2 on one side, a slope of negative 2 on the other side. The slopes don't match, so we do not include the transition point in this derivative, and we would say the derivative is actually undefined. If you want to see what this looks like, these two parabolas are actually, this is going to be x plus 1 squared, and this is x minus 1, or I should say y equals x minus 1 squared. So these are actually the two parabolas that look like this. On one side we have this parabola, and then on the other side, I'll draw it in a different color, we have this parabola. And so the actual function that we care about is like this. So what you can see is it's two parabolas, but they kind of cross each other at an angle. So they do in fact meet at this corner rather than at any sort of smooth curve. So that explains why this function is not differentiable at x equals 0. Just to be clear, what I've shaded in here in blue, this is the actual graph of the piecewise function f of x, or the original function defined in absolute value terms. So, all right, so all that to say, the function is not differentiable at 0. So we can see is that, let's see, f of x has f prime of x does not exist at x equals 0. Now what about the points where f prime of x equals 0? Are there any such points? Well, if you look at it might appear that there are. You might say, well, it certainly looks like they're going to be -1 and +1. The -1 is going to give the top expression a value of 0, and plugging in x equals 1 will give the bottom expression a value of 0. But focus on where these are defined. -1 doesn't apply to the top expression, and +1 doesn't apply to the bottom expression. So if you were just to sort of blindly or naively solve each of these terms for where it's 0, you would conclude that x equals -1 and x equals +1 are critical numbers. But actually they're not. They're actually just because neither of them is in the relevant part of the piecewise function. So if there are no points where, so this has no solutions. In other words, there are no solutions to f prime of x equals 0 just because of the way the piecewise function is defined. So the only critical number is, or the only critical point is x equals 0. And you might say, well, can't I just be naive and just solve each of these for negative, solve each of these expressions for where it's 0 and get x equals -1 and x equals +1? Isn't there just no harm in finding some extra critical numbers? The answer is that you should really understand why this is not, why -1 and +1 are not critical numbers of this function. There's certainly no reason to avoid the understanding, which is far more important than just the technique for solving this on a test. So let's see, 3. We have to evaluate at the endpoints and the critical points. So negative 2, positive 1, and 0. So f of negative 2, we'll put all of those in here. At f of negative 2, we have, let's go back to the original function. That's going to be negative 2 squared is 4, plus the 2 times negative 2 is negative 4. Its absolute value is 4, so I have 4 plus 1, and that gives me 9. And at 0, I have 0 plus 0 plus 1, which gives me 1. And at 1, I have 1 plus 2 plus 1, and that gives 4. So what we can see is that the highest and lowest values are 9 and 1, and therefore we conclude that there is an absolute max of 9 and an absolute min of 1. And by the way, I didn't ask for the location in this problem, so that's the correct answer. An incorrect answer, even though we can certainly find where this occurs, we could say is that here we have, let's see, here we could say that at negative 2, that's the point. I didn't draw it fully in there like that, but that's the point where the absolute max occurs. And we could also say that at 1, this is the point, that's 1, this is the point 1, 4. We could say that those are actually the points where the absolute min and max occur. If I ask you for the absolute max and you answer negative 2 comma 9, that's a wrong answer. An absolute maximum value is a y value. It's not a point or pair of values. You might say, well, isn't it great? I'm just giving you more information. The answer is no. If we ask you for the absolute maximum of something and you give us a pair of numbers, then it's showing that you don't know what the absolute maximum is. So you want to keep straight in your mind that there is a difference between the absolute maximum value, which is a y value, and the location at which the absolute maximum occurs, which is an x value. Same, of course, for minimum.